Testing on YouTube. 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 Come on. Testing on YouTube. All right, we're working on YouTube. The last one is X. Testing on X. Testing on X. The last one is X. Testing on X. Testing on X. Testing on X. Testing. All right, I think we're live. Testing on X. Perfect. It's working on all of the streaming platforms. Let me spit out this gum and then we'll get started. Starting a little early. I'm like all over the place with these start times now, but you know, it doesn't matter. Spit out the gum. Drink some water. And blast the horn. Welcome everybody to another Who Post stream. This week we're going to be looking at SAM 2, which is the successor to the Segment Anything model out of Meta, aka Facebook. So, how's it going, Sarah? There's a lot of other content on this paper, you know. It was a bit of a sleepy week. Some people are starting to get the GPT-4 voice mode, but I didn't get it yet. So this is probably, I think, the best research this week, which is another open source release by Meta, which is kind of killing it in the open source world right now. You know, they're kind of the open source AI company. And this is a segmentation model. So a segmentation model segments images and videos. So you take an image and a video kind of like this, and you create these kind of like masks, you know, basically connected area of pixels that are all semantically related to one another. And that's kind of the purpose of doing that. Why do you want to do this? Well, you could do it for removing backgrounds, extracting specific things from videos and images, so you can do kind of media editing. It's also used for robotics, autonomous vehicles, kind of any use case where you have to do some kind of understanding about the world and understand what the different things are. So still definitely a lot of uses for segmentation, and this is basically the state-of-the-art segmentation model, and it's open source. So we got to thank Meta for that. They got some pretty good names on this as well. I think this is the guy behind YOLO. I'm not 100% sure. Okay. How's it going, Jonathan? How's it going, Ed? Let's start off with the abstract here. We present Segment Anything Model 2, SAM2, a foundation model towards solving promptable visual segmentation in images and videos. Keyword there, promptable. So it's not just kind of blindly segmenting. You can prompt it to segment, and we're going to see specifically what kind of prompting they mean here. What is the application? Robotics, autonomous vehicles, scene understanding, and then any kind of video editing. So I have a version of it kind of pulled up here. This is not Segment Anything 2, but this is a similar, this is the same task. So this is promptable video segmentation. This is the promptable video segmentation that is used in Runway ML, which is right now kind of popular for their Gen 3, which is the image to video or text to video model. But they have, I don't exactly know what model they're using for this, but I bet you it's SAM version 1. That's kind of my guess. But you can see here it says click on an area to start masking. Here's a little video of a little robot toy. This is a sneak peek for a project that I'll be presenting later this next week. But you can see what it wants is a prompt, and the prompt that I'm going to give it is a point. So I'm going to click on one point in the video, and you can see here it's already starting to generate a mask. So you can see it masked out this area, but I don't want to just segment this part. I also want maybe the hand and this face, and I also want this screen, and I want this microphone, and I want this hand, right? So as you can see, it's kind of propagating through the video. So if I go into kind of down in this frame, it still hasn't really done anything, but I can go and I can add prompts over the course of this video, right? So you see I'm just kind of clicking around, and you can see how every time I click, it kind of propagates through all the frames of the video. So I think this is a pretty good little demonstration of what promptable video segmentation is. I'm pretty sure this is not segment anything 2, because that would be extremely fast from Runway ML to have it already integrated into their tools, but I think this is segment anything 1. But this is an example of what you could do with a segmentation model, is basically extract kind of a foreground, background, and then use that in some kind of video editing project. Okay, going back to the paper. We built a data engine which improves model and data via user interaction to collect the largest video segmentation dataset to date. And this is what the Segment Anything Model 1 did very well, is they basically had the biggest dataset, and they had this kind of like interactive annotation pipeline where people and annotators that were paid to do this sat there and they kind of like clicked on these points and corrected these masks, and they built upon that in this second version of the model, right? And I think this idea of like data engines where you have annotators working in tandem, and it's kind of like this complicated UI that uses humans to kind of more filter than necessarily create masks from scratch, which is how people used to do that. People used to click and create polygon masks from scratch. Let me show you guys a video of a polygon mask segmentation. Yeah, so people used to create these from scratch like this, right? They would literally click and create these polygons. That's how a lot of the original segmentation data sets were created, but that's extremely tedious. So now what people do is, and the segmentation models are good enough that they're basically pre-segmented by some segmentation model, and then the annotators come and correct it. And I think this idea of data engines goes beyond just segmentation and video annotation. This is also the case with things like RLHF, and even generating images. Now you see a lot of kind of fancy data engines where you have annotators that sit there and they pick and they annotate, they correct captions. So as these foundation models get more and more powerful, I think the prevalence of like these weird interactive data engines to create kind of an infinite flywheel of training data are going to become more and more popular. Uses a transformer architecture, which is pretty standard, right? Little vision transformer. That's what everybody uses nowadays for vision stuff. But the interesting thing here in this paper that really made me want to stream about this is this streaming memory for real-time video processing. So it kind of feels a lot like a little RNN or an LSTM or even something like a Mamba, right? Where basically, rather than some kind of segmentation technique which encodes the entire video and then basically has some kind of representation of the video and it's working on something like that in kind of like a very linear way, this one has a little memory bank where it'll encode each individual frame. It'll kind of create the masks on that individual frame, and then it'll encode those little masks into some kind of memory with some kind of like encoded representation of like this mask on this kind of area of the image for this kind of frame. And then it stores these in these memory banks. And then that memory bank is used for subsequent frames to help create the masks again. And this is how they create consistent masks throughout an entire video. But this design where you have a kind of cache of memory that is all in some kind of vector representation, right? Some kind of embedding. That idea is, I think, very powerful. And again, it's a very similar idea to what things like Mambas and RNNs and LSTMs do, right? Where they're basically, they're a little bit more complicated because they'll have like forget gates, input gates, you know, they're kind of changing the information that gets stored in this memory, but the idea of having like a memory for the um, system to store information and pull information from, I think that's a pretty cool idea. SAM2 is pretty strong, uses 3 times fewer interactions. Interactions basically just means whenever I click on a point here, right, so I can say, I don't want that, I don't want that, right? That's 1 interaction, so 3 times less interactions than SAM1. Our model is 6 times faster than the original Segment Anything model, which is quite a bit faster. They actually attribute most of that to the image encoder, so I think later on here, they mention that the image encoder size is basically the reason that it can be so fast. I think it's right here. When interacting with the video, the model provides an instance response on the frame being prompted. So each frame is fed through the image encoder. Where is that sentence? Yeah. I think right here. We compare the accuracy of SAM2. Tremendous benefit from adding our trading data engine, whatever. Let me just go through this paper in tandem rather than trying to find... here we go. So SAM2 achieves higher accuracy than SAM1. They're using the mean IOU, which is basically just intersection of how much the ground truth mask and the predicted mask, without using any extra data while being 6 times faster. This is mainly attributed to the smaller but more effective HERA, which is... hierarchical, it's like a shortening of that word, image encoder. So the HERA image encoder is why it's significantly faster. I actually have here pulled up the actual diagram. So this is the HERA repo for HERA, a fast, powerful, and simple hierarchical vision transformer. So you can see here it has multiple levels of hierarchy, right? So kind of like this is wide but shallow, and this is narrow but deep, right? And you can see here it's kind of trained on some kind of masked reconstruction task. Okay, let's go back to the top here. How's it going? Sagar, Skulatom, Aditya, Brian, Fabian, and Siraj. Question from Aditya. How can I download IEEE Explore papers for free? Nothing seems to be working for this paper. Yeah, I think it's really annoying to get papers from journal sites. There's ways to rip it off. Like, I think if you search the name of the thing and then .pdf, sometimes you can find it, but I don't know. There's also people that get paid by these journaling companies to make it very difficult to find the paper outside of the journal website, you know, because they literally, that's how they make their money, is they have to charge you. So you're up against financial interests. Okay, Segment Anything is a universal visual segmentation system applicable to both images and videos. It determines the spatiotemporal extent of entities, right? So because it has this external memory bank, even though it's reading the video as each frame individually and encoding each image individually, whenever it actually tries to figure out what the masks are, it's using the information from previous masks that has been encoded, right? And then it uses that to basically track masks in a spatiotemporal way. Right, temporal just means over time, and then spatio means like within the actual image, and within the actual image is using position embeddings, 2D rope embeddings to actually know where that mask is in the image. Why is this difficult? Obviously, video segmentation is pretty difficult. This one is kind of easy, right, because I'm not really doing anything. The video is static, but you can imagine a much more complicated version of this task where I'm like kind of like moving the camera around and this little robot is going in and out of frame, right? So here we can see, let me add some more points here so it knows to segment this. This is something hard to segment because it just has so many little individual pieces. You see that? Okay. Videos often have lower quality due to camera motion, blur, and lower resolution. Videos are hard. A segment of interest for which the spatiotemporal mask, they're calling these masklets. So the masklet is each individual mask. SAM2 is equipped with a memory that stores information about the object and previous interactions, which I think is the coolest part of this entire paper. Allows it to generate masklet predictions throughout the whole video and effectively correct these based on a stored memory context of the object from previously observed frames, right? So that memory is storing this encoded information for each object. Here's the figure 1. Video and prompts for one or multiple frames. So we got a box prompt. Nobody really uses these box prompts anymore. Like, honestly, I feel like the day of bounding boxes is long gone, you know? Points seem to be the kind of new way to prompt, but you can also prompt with text. I think the original SAM v1 had text-based prompting, but this one doesn't seem to have that, which is skipped. I don't know what skipped means. I guess this one doesn't have text prompting. Okay, but once you get that prompt, it goes into the prompt encoder. The prompt encoder, the reason you need to have this prompt encoder is because to support multiple types of prompts, you want them all to kind of become the same. So this prompt encoder takes kind of a arbitrary prompt and turns it into some prompt encoded version of that prompt that the mask decoder can interpret. And hopefully it's consistent across these different types of prompts. Then you got the individual frame goes through this image encoder, and then it goes into this memory attention where you have the cross attention with the existing memory bank. And then this process just repeats over and over and over and over and over and over, and it just keeps segmenting each individual frame in the video. And here's the data engine and dataset. So this is the actual kind of annotation process. So they release another big video segmentation dataset here with over 600K masklets, which is individual little masked objects. 196 hours, which doesn't really seem like a lot, to be honest, but somehow they get state-of-the-art with that. You can see the model annotates its own data, then you have some human that annotates it and fixes it, and then that gets put back into the model, trains it, the model becomes better, then the model does its own segmentation again, then you have a bunch of humans annotating, fixing it, and then it goes, and that's the kind of infinite data flywheel there. And this is kind of only really possible because humans are still really, really good at segmentation, right? And when you think about the other data flywheels that we've seen, specifically, for example, the synthetic data generation flywheels for code generation, it's very difficult for a human to sit there and like look at a bunch of code and be like, yeah, this is good or this is bad, right? It's like human evaluators and annotation for fixing things like code or even like more complicated text can get very tedious, and you're going to start to have to hire even more and more high-level humans to like do that. So you don't really see this type of flywheel. But for segmentation, even someone who has absolutely no education and is like in some third world country getting paid cents on the dollar, they're still going to be able to segment better than a segmentation model. So this data flywheel is really only possible because humans are extremely good at separating out visual objects in a image. So that's why you can do this. Our data engine generates training data by using our model in the loop with annotators to interactively annotate new and challenging data. Our data engine with SAM2 is 8 times faster. And ultimately they create this segment anything video dataset, which is 35 million masks. Releasing our work under permissive open licenses. So SAM is available, and you can probably see that it will be built into any of the kind of video editing tools such as Runway ML here. Again, I don't think this is Segment Anything 2. I think this is just Segment Anything 1, but there's probably someone at Runway ML right now working on getting Segment Anything 2 into this version, into this tool. All right. Segmentation with flexible prompting. They did get rid of the text-based prompting, though, right? The SAM1. If you look at the original SAM1 segmentation, yeah, this is the original one. Decline. Can I go to the paper? Read the paper. I just want to confirm that they do have the text-based prompt. Yeah, here you go. This is what they removed. So you used to be able to prompt it with this text like that, but I don't know why they got rid of that. I guess no one used it. right? Now all you have is max points and boxes rather than having language in there. I think part of it was that whenever you had this language-based prompting, you have to basically include a language encoder, like a text encoder. And having a text encoder here is probably unnecessarily slow, right? Versus if you got rid of that, this thing here, this prompt encoder, you could probably make it much smaller and it runs faster. And then they probably realized that nobody was using the text encoding anyways, so, or the text prompting. So that's my guess, but I don't have any secret insight. I don't work at Meta. All right, what are we talking about here? Click-based input. We talk about video segmentation. Here's kind of what I was showing you guys, how interactive segmentation works, right? You click on points that are part of the thing, points that aren't part of the thing, and then you can kind of over time refine, right? So if we go back to here, right, like we can zoom in here. You see how this arm here is not segmented? So I can say, okay, I actually want this little arm, so I click on that, and now it knows, okay, this arm is part of that, and you can see it's been propagated throughout the video. So this one is still not confused. You see, it still thinks it's just that part, so I can just say, okay, I do want that, right? This is definitely not Sam 2. You can tell it still has a hard time with that little arm on the microphone. Oh, you see, there you go. There, it got it. So once you add enough of these prompts, it'll kind of figure it out eventually. Let's put another point there. Point-based prompting is the future, I suppose, or maybe not. I think point-based prompting is kind of like bounding boxes. It'll have its golden days, which are probably now, and then over time it'll disappear. Prompts can be negative or positive. After receiving initial prompts, the model should propagate these prompts to obtain the masklet of the object across the entire video, right? And propagating just means it kind of goes through each frame in the video. And this is this note I have here: workflow engineering becomes agent engineering. So this isn't like a single model anymore, right? This is like a bunch of different little models. There's an external memory bank. There's kind of an assumption that you're going to be providing clicks. So we're almost talking about like this workflow, and it's almost becoming like this kind of almost like agentic workflow where you're working together with this AI, and there's a whole kind of like language of interactions. I don't know how else to say that in a way that's less fancy, but I think this is showing what the beginning of agentic workflows could look like. Where are we at? Were we here? Flexible prompting here, click-based inputs. The role of memory attention is to condition the current frame features on the past frame features and predictions, as well as on any new prompts, right? Conditioning the current frame feature. So this memory attention, it's receiving the encoded image, right? So such as some big vector that represents the content of the image, and then it's also receiving this memory bank, which is also just a bunch of vectors that represent the previous mask. So this memory attention here, the negative of that is that now you have to train it with that. So actually, whenever you train this model, you have to effectively include this memory in there. So it's kind of like it's the same reason that training LSTMs or RNNs are annoying, because you have to recreate this memory at train time. But I still think the memory abstraction is a pretty strong idea, and I think it'll pop up everywhere. Decoder. The memory encoder generates a memory by downsampling the output mask using a convolutional module and summing it element-wise with the unconditioned frame embedding from the image encoder. So this seems a little kind of weird, but I guess it makes it work. The memory bank retains information about the past predictions for the target video, maintaining a first-in, first-out queue of memories of up to n recent frames, and stores the information from prompt into also in a FIFO queue up to m prompted frames. Okay. We store a list of object pointers as a lightweight vectors for high-level semantic information of the object to segment based on mass decoder. So the object pointers are basically just a representation of like, okay, this specific information about this mask that I'm putting in this memory bank, this is the specific object that it corresponds to. Just so this memory attention here can be like, okay, there's some information about the image that's coming in through this image encoder, and it wants to know which of the things in that correspond to the object here, right? So it needs to basically redo this mapping from the stuff in the memory bank to the stuff in the image. And that's why you have this concept of an object pointer. Our memory attention cross-attends to both the spatial memory and these object pointers. So this attention here, right? It's doing basically, it's a transformer that's cross-attending to the features here in the memory and the features coming in through the image encoder. Sam didn't share the text prompt part. There's so few people here, you won't know if it's a police setup. I don't know what that means. Are you trying to tell me that the police are trying to honey trap me into something? Police setup? What? Are you telling me I'm some kind of like agent? I don't know what you mean by that. I'm not promoting anything. Them, the people, the watchers. Okay, I don't get it. I'm sorry. I'm too weird. I'm too autistic to understand your joke. 3 phases. Initial phased, use the image-based interactive SAM. Phase 2, now you add SAM into the loop. So now the SAM model is segmenting its own data to create the data that the annotators fix. And then in phase 3, they use the fully featured SAM to basically segment its own data. So the model creates the data that it trains on. Introduce a verification step. A separate set of annotators are tasked with verifying the quality as satisfactory or unsatisfactory. I think they actually have a picture of what the annotators see. So yeah, rather than reading that, let's look at the figure, which is I think a better way of doing it. So step 1, watch the video to identify the objects to track. So it still needs to basically encode every single frame in the video, right? So it's going to run this image encoder through every single frame. The benefit of that is that you can treat every single frame separately. The negative of that is that, right, if you had some kind of video encoder that ate the whole video, that would be faster. But in this case, treating the video as a sequence of frames is more powerful, and then being able to encode them, each of them separately. Run SAM2 on selected object to identify tracking failures. Existing manual or auto-annotated masklets will be pre-filled. Another benefit of doing this is that you don't need to constantly run this image encoder, right? You only run it once on every single frame at the beginning, and then all of the other stuff is just this, right? And that also helps for training as well. So whenever you're training this model, you don't need to be constantly running this image encoder. You basically take your entire training data set, you run it through the image encoder, and then that's it, right? And then you can just basically sample batches of encoded images and then run this part and train this part, which is the part that you really kind of want to train. This image encoder here, I don't even know if they push gradients into it. I think they might literally just use the trained version here, right? So it's a good way to save on training cost. We here. Analysis. No, we were down here. That's where we were doing. We're reading this. Existing manual or annotated masklets are pre-filled in red. Okay, so it gets basically all the masks. Here they're saying it lost track. This is where you have annotator A, who identifies tracking failures, and then annotator B checks through each frames, fixes when added, reruns SAM2. And in this case, right, whenever it says rerun SAM2, that's not even running the image encoder. All this annotator can rerun is the kind of memory attention, and the prompt encoding, and then the actual thing that segments out. So it makes this part of the model very quick and easy to run which is what you want for a kind of interactive workflow like this, right? You want that part to be very quick to run. Question from Kong. What about the inference process? The inference process is basically going to be this as well, right? Like, in fact, this almost more represents inference than it does training. But in inference, you're going to either feed an image or you're going to feed a video. If you feed a video, it gets chunked into frames, and then each frame gets fed separately. If you just have a single image, then it's not using this memory at all, right? If you just have a single image, then you don't need this memory encoder or this memory bank because it's just a single image. The memory encoder and the memory bank is just so that it can use that information to annotate the next frame in the video given what it learned in the first frame of the video, right? So in the first frame of the video, it created some annotations and some masks, and those masks get fed back into the second frame of the video so that this memory attention can say, oh, okay, actually here's the previous masks from the previous frame, and that allows it to kind of propagate the same mask over the entire video. What do you mean with the memory abstraction? I'm talking about this memory bank right here, which reminds me a lot of the kind of hidden state or memory abstractions that you see in things like LSTMs or even transformers, autoregressive transformers, LLMs. You can think of the KV cache as a similar kind of idea, right? That's something I learned in the Mamba. There was a talk that one of the Mamba paper authors gave where he basically made this very clear to me that like the KV cache, the hidden state, like all these kind of memory banks, they're kind of the same idea, just through a different lens. Can these memory blocks be trained individually in some other setting and then be adapted to this setting? Not really. Like the information in this memory is very bespoke for this exact task, right? Like as they were saying here, like the actual every little row in that memory bank, every little memory, I guess, masklet in that memory bank is very specifically like it has like an object pointer. It has this thing here, downsampling the output mask, adding it to the unconditioned frame embedding from the image encoder. So it's really just a concatenate. It's a bunch of information concatenated together, and then that long piece of information represents that specific masklet. So you can really think of it just like kind of like a list of all the masks where little chunks of each of that are different chunks of it, right? Like there's going to be a chunk of it that's the actual position embedding, and then there's going to be a chunk of it that's like the semantic information of what's inside that mask. Then there's a chunk of it that's the actual mask itself, and then there's a chunk of it that's the object pointer. Would be very happy if you could show or explain the implementation of a memory attention. They do have the code here, so I do have the code pulled up. We can actually try to find it. It's probably going to be inside the SAM too. Image predictor, video predictor. So here inside the video predictor, there's going to be some kind of memory, right? Where is it? Let's see if we can find it. Let's see if we control F memory. Run mem encoder. You see this right here? Run single frame of inference. Okay. If run mem encoder, there we go, boom. Get empty mask pointer. There's the pointer. Okay. So where is it adding it to the memory? Here we go, mask mem features. So this run memory encoder, this is the actual, it's taking the current state of inference, the frame IDX. And there you go, there's the mask mem features and then the position encoding. So the position encoding, I think is just, if we actually go to this, run memory encoder. Run the memory encoder on high-res masks. So the memory encoder is here, and you're running it on masks, right? So masks are basically going to be binary images that are either black or white. And basically everything is black except for the actual part of the object that you're segmenting. So for every single mask in this image, you're going to have a separate this thing, mask, right? That's why it's masks with an S, because like if there's 100 objects in your frame, they're going to have 100 of these masks. Change their memory, also to be computed again. Encode new memory. So here you go. You see how it's consuming the current vision features. Current vision features is probably what's coming out of this, right? So whatever it's coming out of this, which is the semantic information. High-res mask. Let's go into the encode new memory. Encode new memory. It's taking your current vision features, the feature sizes, so the height and width of the features, non-overlapping masks for mem encoding. So I guess they have an option here where the masks in the memory encoder, they can either overlap or not overlap, because some of these masks are going to potentially overlap. That's something we saw in the original Segment Anything paper as well, where the masks that were coming out were sometimes overlapping. I think they have an example here because they had this whole like part whole kind of abstraction. Yeah, this thing here. Let me go down. Let me go down. Nope. Go down. Oh my god, dude, this PDF is destroying my computer. Here we go. You see here how, in this case, there would be an overlap here between these masks. This mask and this mask would have significant overlap because they're basically segmenting the same object. So that's probably what this is here. Binarize. Scale the raw mask logits with temperature. Apply scale, and then there you go. Mask mem position encoding. Where's the position encoding? Mask mem out. Self memory encoder. All right, we're getting deeper. We're finally getting to the memory encoder. Boom. Memory encoder. No, we want the actual memory encoder. Memory encoder. Okay, so memory encoder is like separately loaded. SAM2 modeling. SAM. Mask decoder, prompt encoder. We want memory encoder, this one. So this is the actual memory encoder. Lightly adapted from ConvNext. Ah, that's kind of cool. ConvNext is a ConvNet that was designed to basically compete with vision transformers. Whenever this paper came out, they basically showed that, hey, vision transformers aren't going to necessarily just always beat ConvNets, and really it's more about the data, right? And ConvNext is basically just one of the more modern ConvNets that, given the same data, will probably achieve about the same score as a vision transformer. But I think vision transformers still kind of edge out ConvNets, but if you're going to use a ConvNet, ConvNext is pretty good. And you can go, here's the actual memory encoding. So it's not even that complicated. You see, it's really just a ConvNet, whatever this fuser is here. And then here the memory encoder is composed of that ConvNet. And then the fuser. And if we look at the forward, so this is what actually happens when you have the inference, right? You have your pixel features, you have your masks. It takes your pixel features, runs it through that ConvNet. Then it takes X, fuses it with the masks, and then you add the position encoding. And the position encoding, I think, is the 2D rope they said it was. Let's see. Position encoding equals position encoding. Position encoding, where does this get used? Class memory encoder. See, this is hard because now I need to figure out where this gets used in order to actually see. Search for this symbol. Memory encoding. Here we go. Position encoding. SAM2 modeling position encoding position embedding sign. So this is the actual position embedding for the memory. I don't know. Hopefully that helped, but I don't know if it did. KV cache, you mean the key value attention map is like a memory? Yeah, this is something that the Mamba to KV cache is memory. Mamba Explained, I think is this one. No, it's not this. There's a blog post made by the Mamba 2. Yeah, this guy. So this is the author. And then he has state space duality. KV cache. It might have just been in the podcast. There was a podcast version of this. He goes on some podcasts and he explains this, but he makes the analogy that the KV cache is similar-ish to the hidden states in Mambas, which is kind of this idea of a memory, right? You're storing some information to do something in the next prediction. Okay. Where were we? I think we were here. Dataset distribution. So this is where all the datasets come from. So how many males are segmented? Kind of seems a little bit unnecessary, but we used internally available licensed video data to further augment our training data set. So a little bit unfortunate that I think most of the data is public, but kind of like anything AI nowadays, even if it's open source, they're just open sourcing the algorithm, which is this code, and they're open sourcing kind of the training scripts, because I think they do have training scripts as part of this, but they don't really give you the data, especially because some of that data is going to be internal. So they're not going to give you the Facebook data that they trained on, but hey, you know what? They gave us all the code and told us all about the training and released this nice paper, so I'm okay with that. Most of the benchmarks here are going to be using this metric here, this J and F. So this J and F metric is what is used for semi-supervised video object segmentation. So unsupervised video object segmentation would be basically if I didn't provide any clicks, but because I'm providing these little clicks, right? I'm providing a little like click like that, and then the negative clicks, right? Like that makes it semi-supervised because I'm kind of supervising it, but not really. And you can see here, this is Papers with Code. They also have very nice benchmark leaderboards. So you can see here over the years in 2017, this was the strongest model. And now in 2023, they haven't updated it yet, but the Segment Anything 2 is better than this one. So you can actually see here, they mention it. So 2 state-of-the-art models for video augmentation, XMEM++ and Qt. And that actually corresponds here. So you have Qt Plus, which was released in 2023. Here's the code for that if you want it. And then there's also XMEM. So it's probably a slightly older version of XMEM++ from 2022. And here they're saying that they're beating both of them. SAM2 dominates both methods. But back to this J and F metric. So the J and F metric is basically like a metric of metrics of metrics. It's kind of like multiple levels of metrics at this point, which is, it's a little bit confusing. You can see it's the same metric that they're using here. And GPT has a nice little summary for it. J and F metric is a combination of multiple metrics. So you can see J and F is J plus F over 2. So it's like the average of the J and the F. So what are the J and then what is the F? J is basically IOU. IOU is like how much overlap there is between the mask that you predict and the ground truth mask. Right? And then F measure is this precision versus recall, right? So precision is like how accurately are you actually performing this? And then recall is like, hey, can you find the thing in there, or are you missing some of the things in there? So I don't know if I like this metric. I don't like these kind of like combo metrics because they make it hard to interpret, right? You could have something that has the same J and F as something else, but in one of them, the F is really high and the J is really low. And then in another one, the J is really high and the F is really low. So anytime you start combining these metrics into these kind of like super metrics, it becomes a little bit more difficult to interpret, but I can kind of see why they just want a single number here, right? They don't want to have like 17 of these charts with like precision and then recall at 90 and then recall with 5 click and then recall with 1 click. Like there's too many charts there. Just come up with one number, and that's why they did that. But that is what JNF is. How's it going, Christopher? Is the segmentation mask 0 and 1, or are there in-between values? No, and a segmentation mask is just going to be 0s and 1s. I think here, Replicate has a nice example of what it looks like. So Replicate is kind of like a hugging face, but they already have the segment anything too. And this is what I mean by masks. So these are the masks, right? So when you actually go here and you run this, and whenever you run this without clicking on anything, it basically auto clicks on things. So if you scroll down to the appendix, this is what the segment anything 1 paper also did, but just so people understand exactly what's going on here. We prompt the model with a 32 by 32 grid on the first frame, and additionally we use a 16 by 16 grid on 4 zoomed in image crops of the first frame. So if you don't provide any clicks, it'll basically just put a bunch of clicks. It'll put 32 by 32 clicks, and then it'll just go based on that. So you can see how it's kind of segmenting out random things. And then the actual masks that it provides are like this, right? So you can see how there's some overlap. Like this one is basically the same as this one, except it has like a little extra stray pixel there. This one is, so these are pretty good. These are all kind of separate, but there's no kind of guarantee that you're not going to click on the same object and end up with 2 of the masks that are the same. So there is some kind of hard-coded bullshit that they have to do here. For example, we remove tiny disconnected components with area smaller than 200 pixels. We fill holes in segmentation masks if the area of the hole is less than 200 pixels. So I feel like this part still, we need to do some better design here, because to me this is NMS all over again. NMS, for those of you that are a little bit NMS suppression, is something that people used to have to do with these kind of bounding box predictors, where basically bounding box predictors would predict multiple bounding boxes that were overlapped. So you had this additional extra step where you would look at which bounding boxes were overlapping and then use that to refine it to a single bounding box. So basically go from multiple bounding boxes to a single one. And NMS is a bunch of hard-coded settings, right? So it's like how many bounding boxes, how much overlap, and some random human came up with the little hyperparameters for the NMS. And this actually kind of seems very similar to me, right? Where it's like, why 32 by 32, right? Like why 200 pixels as the area, right? So like there's some hard coding here that comes into this, but luckily for us, the hard coding runs on the CPU, so it can run very quickly. But at some point, I feel like all of that should just get simplified, right? Like you ideally don't want to have all these magic hyperparameters here that you have to tune. If you could figure out some way to kind of have all of that be built into the model itself. But I think we're still some time before we can figure out how to do that. All right. We were talking about the JNF. 2 different settings: offline evaluation, where multiple passes are made through a video to select frames to interact with based on the largest model error. So this is how the you're looking at, or what am I trying to say here? Let me just finish here. And then online evaluation, where the frames are annotated in a single forward pass through the video. So online evaluation, you're basically just running through the entire video, right? You're going through the entire video. You're encoding every single frame with your image encoder, and you're accumulating this memory. So whatever you get in that very first frame kind of propagates forward all the way in time, right? So like you do all your clicks, and then it just basically just adds those to the memory, and then gets the next frame, next frame, next frame, next frame, next frame, next frame, keeps adding to that memory. Probably doesn't change the memory very much as you go through the frame, especially for something like this where it's basically just kind of static, right? Like the video is kind of static. Nothing's really changing. That's the online. Offline is multiple passes are made through the video, and you select frames based on the largest video error. So this is kind of, or largest model error, right? Because the model is going to be able to output some confidence, kind of like the original segmentation, or the original segment anything model. It did output this score here, right? So not only is it outputting a mask, but it's also telling you kind of how confident it is in that mask. So I think there's something similar here as well, right? This model error. It might not be explicit, but you can see here, number of annotated frames with 3 click, and then number of annotated frames with 3 clicks. So only 3 clicks. And you can see here, the more frames you annotate, the better the performance. So how many frames you annotate is how many of these frames you go through and you add your little clicks. So you can here, I can come here and I can add clicks. Come here, add clicks, right? And you can see it takes time because it has to propagate those clicks throughout. It is state-of-the-art. It beats the current 2 state-of-the-arts, Qt and XMEM, as we saw here, right? Here's Qt, 88. Sam plus XMEM, Sam plus Qt versus Sam2. It is quite beating them out with one click. Obviously, the more clicks you have, the more you get kind of a convergence there. Generally, I don't necessarily care too much about the fairness evaluation, but I thought this was kind of interesting here. It looked at how whether segmenting people across gender and age and which thing is easier. So one thing I thought was weird here is that, like, look at this. For the age group 18 to 26, compared to the age group of 50, somehow it's significantly easier to detect old people. Like, this is not an insignificant amount here. Like, we're talking like a 10%, maybe not 10%, more like 5% jump between segmenting younger people and old people. So I don't know, maybe if you're in a AI dystopia and the Terminators are wandering the wasteland and they're searching for people to kill, maybe if you have an old person with you, it'll segment the old person first and then you can somehow survive. But I don't know. That's what I got. How's it going? Cesar Cadir Torrico Villanueva from Bolivia. Pretty cool. Nice to meet you. Young people move too fast. Yeah, I wonder if it's something like old people have the white hair. You know, like old people have white hair and the white hair is kind of easier to recognize versus I feel like young people still have their kind of original hair color, which tends to, on average, be darker. So maybe it's that. I don't know. I just thought it was kind of weird. I didn't think it would matter. 1 click and 5 click MIOUs, right? So how many clicks and then what's the intersection over union on a single A100 GPU, which is quite cheap nowadays. I think you could probably rent these for easily less than dollars per hour. So you can run it. I wonder how many A100 GPUs Runway ML is using for this, right? They probably have a dedicated inference server for specifically this masking task, and then all the people who are using Runway ML and using this specific tool, they're all sending their request to that one server that's just sitting there constantly running this segmentation model. Without using any extra data. What am I looking at here? Data is all you need. Yeah, so what I wanted to show here is really the difference between the model architecture and the data, right? So I said data is all you need. And why do I say that? So if you look at SAM versus SAM2, so the original SAM versus the new SAM, right? And the original SAM is actually kind of old at this point. Like, we're talking about, when was this paper released? 2023. So maybe not that old. So like a year of architecture improvements gives you an almost identical score on the same data set. So if you take SAM, the original SAM, and train it on this data set, and then you take the new SAM, which has all the memory and all the extra bullshit. I don't think this one has the memory because this is an image, but it has whatever extra little rope position embeddings and like a bunch of other crap that they put in here. Look at that, 58.1 versus 58.9. So 1 year of improvement in model architecture, if you use the same data set, you almost get roughly the same exact score. Versus SAM2, where, okay, now you account for the new data, which is really the result of this data engine. Look at that, you get a much more significant boost. So, I don't know, this kind of just reinforces our intuitions that we have kind of already built from a bunch of these papers before, that spending time thinking about the data quality, the curriculum that you're using during training, right? Like, how are you feeding this data over the course of training? How do you get humans involved in the loop in order to improve the data quality over time? Like, those type of questions and those type of problems, solving those is going to give you a bigger boost than spending your time trying to think about kind of like, how can we improve this model architecture? I don't know. It's something that I kind of generally always talk about, but I think it's important to mention yet again. Varying image encoder sizes. So the image encoder here, right, which is basically this image encoder, the Hiera. How do you say this? Because it's hierarchical. So really I would say Hiera VIT, but I want to say Hiera VIT. I don't know how to pronounce that. Hierarchical, Hira. So I'm calling it Hira. But the Hira image encoder, obviously the bigger the image encoder, the better the features that come out of it are, right? The more quality they're going to be. But the problem with that is that the bigger the image encoder, the longer it's going to take to run, right? So like if you use a huge image encoder, like I'm going to be sitting here waiting for the image encoder to encode every single fucking frame, and it's going to take fucking forever. So there's a balance there that you want where, hey, if someone's just like using a little like face tool on like their little cell phone, like you don't want it to take super long. So being able to trade off the speed versus accuracy by using different image encoder sizes makes a lot of sense. Using a larger image encoder brings significant accuracy gains across the board. Here's your JNF metric across a variety of different data sets here. This is visual object segmentation. I think that's what this stands for, VOS. We evaluate on our MOSE development set, which contains 200 randomly sampled videos. We compare the accuracy of SAM2 when trained on different data mixtures. We fix the number of iterations and batch size with only the training data changing between experiments. We find a tremendous benefit from adding our data engine into the training mix. Let's go back to that. Data is all you need, guys. How do you make the data better? That's what you should be asking yourself every day. How do I make this data higher quality? How do I get more data? How do I get human annotators involved in this process to clean the data? How do I get the model itself to somehow pre-annotate or sort the, like filter the data in some way, like produce some kind of artifact that allows the annotators to also fix that, right? Like the data questions are the most important questions you should be asking yourself. This is more showing that, right? So here they have different training data sets. So their data mix, right? So they say, okay, we're doing an ablation here. We want to see how important it is to train on this data versus this data versus this data versus this data. And the one kind of general trend here that I want you to see with these two red boxes is that, look at this. If you look at all the training runs that were done with just an individual data set, these scores tend to be a lot lower than these scores here, right? These are the ones where they trained on either all the data or 3 out of 4 of the data set. So more data is better. One interesting thing here is just how overfit this VOS is to this MOSE data set. Like, look at this. The VOS, it kind of performs like shit for everything except for this MOSE data set. So another kind of story here is that you just have to be careful with the training data and benchmarks, because if your training data can make you think that you get a good score on a specific benchmark, but it's really just because that training data is a little bit overfit to that specific benchmark. So don't rely on any one benchmark or any one data set. There is a consistent power law relationship between the quantity of training data and the video segmentation accuracy on all benchmarks. The more masklets, the higher the zero-shot JNF. Here they have, this is different benchmarks. Segmentation accuracy for video and image. Oh, yeah, this part here, I thought this was kind of interesting. So they're doing ablations here, right? So they're basically trying, ablating all the different parameters of this model, right? So the resolution of the image, how many frames you're annotating. But one of the interesting ablations that they did here is in the memory channels, right? So the memory channels, you can basically think of it like inside this memory bank, how many numbers are there in that vector that represents that specific masklet, right? So 256 means you have a lot more capacity, right? You can store a lot more information about that specific masklet, right? So intuitively, it would make sense that, okay, if you go from 64 to 256, now you should have a lot more capacity to store more information about that specific masklet, which should somehow make it more accurate at the end when you're just looking at the accuracy of the masks themselves. But one interesting thing that I saw here is that it doesn't actually seem to matter that much. 64 versus 256, like, you don't need the 256. So that was kind of interesting, where it's like we're already, at least for this specific version of the task with this specific image encoder and this specific thing, like, you don't need to be storing a very large chunk of information for each individual masklet in that memory. You can actually keep a very small channel. And because this here is being stored and fed in every single frame, if you make this small, it's going to be a lot faster. So I think that the TLDR of this paper is that it's better than SAM1, but in terms of like the actual quality is just like a little bit better. Where it really shines is just the speed. So it's really significantly faster, which is important because, like I said, like the speed matters, right? Like the fact that I have to sit here and sometimes wait, right? Like here, if I click on that, you see now it has to go and it has to propagate through. So you see every single one of these, it's loading because it has to propagate that change that I made through it. Right? See, I've got to click on more of these. It's very pleasing to click. Point-based annotation is surprisingly kind of fun. Here's another unfortunate hyperparameter here. They have to cap the number of memories. So there's some limited size to that FIFO queue of memories. Higher resolution leads to significant improvement across image and video tasks. That's probably pretty standard. We also see that with vision language models, right? Any kind of vision-based task, if you increase the resolution of the image, you're going to get a better performance. Scaling the backbone brings gains on both image and video metrics, while scaling the memory-only attention only improves video metrics. So scaling the backbone is the image encoder. So they're basically saying if you make this image encoder better, it improves the video segmentation, also improves the image segmentation, basically improves everything because bigger image encoder is able to get more information out of this image, better represent the image, compress it in a less lossy way. Absolute position encoding in both the image encoder as well as the memory attention. So for the memory, the position encoding is important because basically you need to have some kind of positional information, right? You need to not only encode this mask, but you also kind of need to say, where is this mask in the image? So the same way that in a VIT transformer, right, in a vision transformer, whenever you feed an image to a vision transformer, you have to feed it these little position embeddings so that the transformer kind of knows where in the image this little individual patch was. So there's kind of a similar thing here, right, where you need to have some kind of positional information for each of these masks, and they're just going to use a pretty standard rope encoder, which we have a video for as well. Here's the actual. In addition to sinusoidal absolute position embeddings, we use 2D spatial rotary positional embeddings in self-attention and cross-attention. So this is the mask decoder. The mask decoder is this one, this thing here. So the mask decoder is consuming the encoded prompts, and then it's consuming what's coming out of this cross-attention module here that looks at the encoded image and then the encoded memories. So the mask decoder is what actually creates these masks. So if we actually go back to that, you see here the masks. It's per mask. Here's your MLP with the score. Right, so a little multi-layer perceptron, which is just a little, probably just 2 layers of fully connected neurons, and that outputs the score. And the score is then used to filter. So you can look at the score as kind of a proxy for how good it's performing, which goes back to this thing here, right? Largest model error. Here's the image embedding. So you can see you've taken your image, which is a 3-channel image, 1024 by 1024, something like that. by 3, and now you've turned it into 256 by 64 by 64. So it's like a little tiny little thumbnail that's very deep. Here's your cross attention here. So you're letting the image and then the, I guess it's not cross attention. Use the mask token corresponding to the output as the object pointer and generate an occlusion score, which indicates if the object is visible in the current frame. Oh shit, look at this. Huh, that's actually kind of super interesting. So there's also this occlusion token. So if you have a video where the thing goes in and out of frame, so like let's say you have this dog video and then halfway through the dog closes its mouth so the tongue is no longer visible, it'll still have the tongue masklet inside this memory bank, but it will just have an occlusion of like, I guess 1. I don't know if it's like a 1 to 0 kind of thing, but yeah, that's clever. Right, so it allows you to keep track of objects even if they drop out of the frame or drop out of the video and go into the video. And the actual object pointer is just simply what's coming out of this attention block here. Why do they make it go out before this MLP here? Have I looked into what the dataset looks like? The dataset is just going to be videos. I don't know specifically. They have like the actual data mix somewhere over here. Yeah. 1.3% Davis, Moz, YouTube VOS, SA1B. I think this is the Segment Anything 1B. This is the original Segment Anything. SAV, this is the new Segment Anything dataset. And then 15% secret sauce internal data. I should probably do that. You know, that's something that Karpathy recommended. He says, hey, one thing that really made me understand ImageNet better, which was actually going through it. So like he actually went through ImageNet and like image by image and realized that a lot of it is just these dogs. So, you know, maybe if you're doing this type of stuff, it's worth actually going into the fucking Davis data set and like actually looking at the videos in there and seeing what they are. Like, is it always just videos of people? Is the camera generally static? Are people coming in and out of frame? Like, how complicated are these different data sets? How different are they? It's probably worth looking into. But no, I haven't necessarily done that. I'm giving advice that I don't necessarily follow myself. Question from Patrick. Couldn't they just use synthetic data sets? Kind of. I mean, they are using a synthetic data set, right? It's like the model is generating the masks. So in phase 2 of the training, the model effectively generates its own masks. So like in a way, I wouldn't call it like a fully synthetic data set. It's not like you're generating the images with some kind of image generation model and then segmenting those images with a segmentation model and then using that. So that, I would say that's like kind of a fully synthetic data set. This is like kind of a partially synthetic data set where it's like you're using a model to generate the mask and then the human sometimes fixes the mask. I wouldn't even, maybe the word synthetic there is not correct as well, because in that case, the model's not, I wouldn't say it's synthetically generating the mask. I would just say it's like semi-supervised, I think is the best way to describe it. The memory of the first frame is included in the entire video. It is possible to limit this memory to like X frames. Yeah. Depends on where you put which frame you annotate, right? So it doesn't necessarily need to be the beginning of the video, and they actually mention an augmentation that they do. Let me see if I can find it. Yeah, so for example here, we reverse the temporal order with a probability of 50% to help generation to bidirectional propagation, right? So we train by simulating an interactive setting sampling 8-frame sequences by randomly selecting up to 2 frames for corrective click. So why do they need to do this? The reason they need to do this is because sometimes, right? Let's say that I was redoing this, right? And rather than starting with the very first frame, I just decided to go to 15 seconds in, and then this is where I provided all my annotations, right? This is where I clicked around. If I did that, then the model would basically now need to create the memory here and then go back and annotate all the frames backwards in times, right? So the model doesn't necessarily care about this abstraction of like forward in time and backward in time. Really what it's doing is it just has some annotated frame, and then it's outputting the masklets, putting them in some memory there, and then it's going to propagating out from both directions from that, and then just annotating subsequent frames. So the memory itself is not necessarily, there's no like temporal notion there of like, oh, this is going forward in time. It's like, it's just basically saying, okay, here's what I have in this frame. Okay, let me do the next frame. And it could be backwards in times or forwards in times. And in order to be flexible to that, they basically have to augment the data set. So 50% of the time when you're feeding a particular video into the training process, it's like flipped. So it's like the video backwards. So it's equally effective going forward and backward in time, using the memory to create annotations for a frame given a previous frame, whether that previous frame is forward or backwards in time, whether it's propagating backwards or forward in time, which I think is good, right? It's like you're ignoring time because it doesn't really matter for the task of video segmentation. Video segmentation should work equally well backward in time and forward in time. How does synthetic dataset create quality dataset? Models can hallucinate or create more than 6 fingers. Yeah, anytime you're using synthetic data, you have to have some way of improving the quality of the data over time, because or else it'll basically deteriorate, kind of like you're saying, right? Like the hallucinations will spawn more hallucinations and kind of just like fuzzes out. The reason you can solve that is because, for example, with something like code, you can evaluate, you can actually run the code that the model generated, and actually the code that doesn't work gets removed, right? So you can say, okay, here's some code that I generated. It doesn't actually work, therefore I'm not going to train on that, right? So you have this method of evaluating code that you've generated. In this case, you don't have necessarily any way of evaluating whether the mask that was generated is correct or not. So in order to do that, you have to use a human, right? So in this case, the way that you validate whether the masks that are being generated are worth training on is by having some humans sitting in a room looking at this and clicking on these buttons, right? So they click satisfactory or not satisfactory or reject, right? So like if it clicks satisfactory, then this is going to go back into the training pool and the model's going to train on it. If they hit reject, it's not going to go into the training pool. Rendering video from high quality 3D models. Sounds like a cool idea. All right, let's go deeper. We must go deeper. Talking about workflow engineering. We train by simulated interactive setting. What else? A linear combination. This is the actual loss. So all the different losses that they use here. So most of it is actually this focal and dice loss for the mask prediction. Then you have MAE for IOU and cross entropy loss for object prediction, right? So a couple different loss functions with a couple different weights in front of them. Interesting that they're using PyTorch 2.3.1 and automatic mixed precision with bfloat 16. So it means that you could probably quantize this even more, right? So there's probably, I wonder if you could run this on an actual like tiny little cell phone here. So you can see here, you take your model, you put it in inference. So here's your model, right? So you're giving it your config, you're giving it the specific checkpoint. Here are the different checkpoints for the different sizes. Here you give it your image, but here you see how they do this torch autocast. So they're basically saying, okay, all the different little parameters of this model I want you to fit them on my GPU, so put them on my CUDA device, my GPU, and I want you to basically put it in bfloat 16. But here, right, you can imagine making this an even smaller data type. I don't know if they necessarily compare that, but people are going to try to do that. And I always mention this, but there was like a SAM quantized distilled. Quantized SAM? Yeah, here you go. So this is, I don't exactly know what this one is, but here's a SAM that was running at 4-bit. So you can actually see here the difference. 16-bit versus 4-bit model size in megabytes. So someone's going to do this exact same thing with this SAM2, right? People are going to figure out how to run it at 4-bit rather than 16. Is there any specific reason of leveraging transformer-based architectures rather than diffusion-based architectures for SAM2 segmentation? There's probably a way to reframe this as some kind of diffusion problem. We might have even read a paper where they try to do segmentation with some kind of diffusion type architecture, but like diffusion kind of seems like not necessarily the right fit for this, you know, especially for something like this where you're kind of like trying to predict masks on the same image over and over again. I don't know. I'm not saying it's not a good idea, because maybe someone goes and figures out some way to reformulate this as a kind of a diffusion problem and it ends up being better than SAM2. So I don't want to like dig my own grave and say that diffusion is not the way to do video segmentation, but yeah, I don't know. I kind of think transformers is a pretty standard good idea here. Could I use, question from Nuno, could I use this model to segment in real time like a t-shirt to infer an in-painting, or how would you imagine this pipeline? I feel like this is probably close to running real time. They don't, let's see if I control F real time here. Real-time video. This doesn't mean you can run it in real time. This is more you can real-time do the whole thing. Consuming video frames as they become available. The image encoder is run once for the entire interaction, and his role is provide unconditional tokens. So like if you wanted to run this in real time, you would have to basically every single frame. So if your camera's running at 30 frames per second, you need this image encoder to basically run 30 frames per second, or maybe you downsample it. But like, I think if you do quantize this and you could probably figure out a way to have this basically segment in real time, but I don't think they necessarily do it in this paper. Returns the segmentation of the object throughout the entire video in near real time. So you see that they don't say actual real time, they say near real time. Limitations. Struggles with accurately tracking objects with very thin or fine details, especially when they are fast moving. That's exactly what we were running into here. You see, remember that? Look at that. Let's make this a little bit smaller just so you can see the, but you see this feature here, this kind of long and thin. That's very hard for segmentation models. Gotta add more point annotations. I want the microphone. Give me the microphone. Maybe I have a future as a data annotator, because I feel like I could just do this shit for free. Look at that. SAM2 processes each object separately using only shared per frame embeddings without inter-object communication. So I think here what they're talking about is that you're not necessarily, this memory bank is like per object, right? It's like a FIFO queue of objects each object or each masklet, you could think of it separately, is a line in this, versus like in something like an LSTM or a Mamba, it's like a basically one giant brick of memories, versus here it's like separated out per object. And the reason they do that, I think, is also so that you can kind of like, if you go to a different frame and you click, right, it doesn't have to redo the whole thing. It just basically only has to redo that specific little mask, that specific object. This is the occlusion MLP. An additional MLP head is applied to this new token to produce a score indicating the likelihood of this object of interest being visible in the current frame. SAM2 predicts multiple masks at each step of the video. If further prompts do not resolve the ambiguity, the model selects the mask with the highest predicted IOU. Our memory encoder does not use an additional image encoder and instead reuses the image embeddings produced by the Hira encoder, which are fused with the predicted mask information to produce memory features. And this is kind of what we saw here. Right, let's go back. Yeah, so the memory encoder is basically taking in the pixel feature. So these pix feet here is this is the image embeddings produced by the Hira encoder. That's this pix feet, and then the fused with the predicted mask information. The predicted mask information is this here, masks. So there's the fusing happening there, and the fuse is literally just, let's see the fuser. Fuser is just literally this. Just projects and then returns. I'll try to convert this into real time for a project. Yeah, that could be something cool. Like I said, it's an easy win. There's probably somebody already doing it. I bet you like somebody's literally done that. If we search this, if we do SAM2 quantized. Because people are pretty fast about these fucking things. Here we go. Segment anything to in ONXS. ONXS is the open neural network. So I bet you, I wonder if they have the... Search for. I'm looking for 4-bit. Nah. You can also distill it. So that's another thing. Distill SAM. Distilled segment anything. Awesome segment anything. This. I'm trying to find a repo. Yeah, here we go. Prompt. I think it might be called Tiny Sam. Let's see. Tiny Sam. Here you go. Tiny segment anything. So they take the original segment anything, they distill it down, and then they distill it down, and then you quantize it. So actually, this is exactly what you need to do, Cesar. Take the segment anything 2 model, distill it down. And when you distill it down, you can actually distill it using whatever specific task. So you can, it's like a distillation, but also kind of a little bit of like a little bit like a fine, like you're kind of like putting it into a very specific task. So like if you know everything is going to be these cow pictures, then you can distill it kind of with those cow pictures, so that the distillation forgets the non-cow picture stuff and kind of only really focuses on that cow picture stuff. This will reduce the total number of parameters, and then once you reduce the total number of parameters, you can take each of those parameters and then quantize them, and then you'll get to something that is significantly faster. And then maybe you can get the real time. But so here you go. So here are the 3 different sizes of the original SAM. and then you get the tiny SAM, and then you get the Q tiny SAM, quantized tiny SAM. So there's going to be the same thing for this, right? People are going to distill this. And this is the benefit of open source, right? Is that Meta doesn't even need to do this. They just release segment anything, and then some other random person in some other random institution is going to distill it and quantize it and then publish. And not only that, but there's going to be like 10 people that are trying to do it as fast as possible so they can be the one with the repo where they do that. So if you open source your stuff, people do all the work for you, you know? Everyone wins. Meta wins. Runway wins, right? Because they get to use it. And then anybody can use this now, which is the benefit. Win to win, yeah. Okay, I don't know what else to talk about. I think I got through most of the stuff that I thought was important here. I think really the cool part about this was the memory bank. Let me sip some water, and then we'll do a little summary. I'll scroll through, see if I missed some questions, and then we'll go and finish this. Question from Cesar. SAM to CPP soon? Yeah, probably. I bet you there's someone working on that. You don't even really need... I wonder if there's a Hira CPP. I don't know. Maybe not worth it. One thing you can do is you can distill into a model that you have implemented in CPP. Old people wear glasses, yeah. All right. That's all I got, guys. Let me do a little summary here. Here's the summary. So today's stream was on the Segment Anything 2 model. Segment Anything 2 is the latest version of the segmentation model that Meta works on. Segmentation models basically break images or videos into semantically similar kind of parts, right? So you can extract individual objects out of videos, whether that's for creating content or whether it's kind of for a robotics use case or some kind of autonomous vehicle use case where you want to pull out individual things from the scene. Maybe not robotics as much, because like, to be honest, in a lot of robotics use cases, I actually think that the way that that's all going is it's going to be like a vision language model. So it's already extracting the information directly from the image. You don't need to do this kind of like multi-stage pipeline where you first segment and then you extract. So I don't know if it's necessarily as important for robotics as it used to be, but segmentation still definitely has a lot of uses. And this is the current state-of-the-art model. So Meta being a good guy Meta and releasing it for everyone to use. So you can expect all your segmentation tools that are built into all the different things that you use, whether it's like Runway or Snapchat or whatever other weird. Adobe is probably going to integrate this. But very similar kind of design to the Segment Anything 1. You still have the basic ideas that you're taking your image, you encode your image, and then you have this idea of like a prompt encoder and then this mask decoder. So very similar design, except now they added this memory bank, which I think is like the coolest part of this, right? So they basically found this is the architecture for the image or the image segmentation, and then they were like, okay, how do we turn this into a video segmentation model? And they were like, okay, well, what if we figure out a way to take the output of this mask decoder, right, which is the individual masks, which is with this, right, a bunch of masks, and turn it into this kind of memory, which you can use to then get the next frame, right? And it works really well. So they basically encode each object, right? They're kind of calling it like a masklet, but they encode it along with information about where the masklet is, along with some other information too, such as whether or not it's visible in the frame, right? What they call an object pointer, so you can kind of, you know which one is which. And then as soon as you label one frame, then it kind of just propagates out to the rest of the video, and it can propagate forward in time, it can propagate backward in time, it doesn't really matter. And I think it's a very nice, clean little solution of adding this memory encoder and this memory bank so that basically their image segmentation model is now effectively a video segmentation model. And they also put a bunch of work in to make this image encoder more efficient. So they're now using, I think in the original one, they probably just, this image encoder here, it's probably just some random VIT, but they replace it with this Hira, this one here, hierarchical vision transformer without the bells and whistles that is fast, and that allows them to run this significantly faster. They also get rid of the text-based encoding for the prompt, which also is going to make this faster because you don't have to be encoding text anymore. You can just go straight to points, which seems like what people are doing. And then the other big thing that they do here is really show you how data is still king, and finding ways to improve the quality of your data and add more data to your training process is really the best way to push the state of the art. And the way that they do it here is by creating what they call this data engine, which is basically just kind of like an application that runs that some human is interacting with, where like the SAM model is like pre-segmenting things, and then the human kind of corrects them, and then that data gets then fed back into the SAM to then train it, and then the next version of the SAM gets put into that little application where you have some guy sitting there clicking, being like, this is good, this is bad, this is good, this is bad, fix this, fix that, this is good. And that little flywheel just keeps turning and turning and turning, producing higher and higher quality data. And that's how you get 6 times or that's how you get higher quality, but the 6 times faster is more, I guess, the model itself. IDK, that's all I got for you guys. I thought it was a cool little paper. I think it's a great tool in the toolbox of the open source community. Is this memory bank can be used in other text-based models for long-term memory, or is it different? It's not like this memory bank is very, very specific to this segmentation use case, right? So it's not like you can take this and use it somewhere else. But the idea of some kind of memory bank where you can store things and pull things from, that is, I think, here to stay, right? And if you blur your eyes enough, right, what is a Mamba doing? It's reading in your input and then changing this little hidden state, right? What is an LSTM doing? It's like removing and adding things from this fixed size cache or memory or hidden state, right? Like, so a model that has somewhere where it can put intermediate things and then pull from those intermediate things to help this current frame, that's kind of the high level thing that I think is going to be basically standard in all the different AIs that you interact with. Any kind of AI product that you interact with, we're going to move away from this kind of like one time, like here's the input, here's the output, and that's it, right? You're basically, every input is going to produce some output. That output is going to get stored or like create some entry in some memory bank somewhere. And then that memory bank is going to be then used to produce the next, along with the next input, to produce the next output, right? Yeah, here's the one that I've seen. Mirasol, Google. Mirasol, Google, multimodal. Yeah, this one. This is a paper that had something that I think, this is more kind of what I'm describing, which I think is more what you're probably interested in right here. So this is a paper by Google called Mirasol 3B, an autoregressive model for time-aligned contextual modalities. I'm pretty sure this is very similar to what GPT-4o kind of voice mode is doing, right? So GPT-4o voice mode, it's consuming video and text, and then it's basically producing text or, in that case, speech, right? But the cool part about this is that it has this kind of memory here. So you see how it's taking these video audio features and then it writes it. So like as it's consuming video chunks and audio chunks and producing text chunks or audio chunks out, it also is writing to this little memory. And then whenever it writes to that little memory, it can read that along with the input. So they call this the token Turing machine combiner. Token Turing machine is a recurrent sequential model with transformers and token-based operations. It maintains an external memory MT as a set of features and updates it at every time step by reading and writing. Give it inputs U at T, it first reads the features and then writes them to this memory. Right? The key idea is to make the TTM processor generate the outputs by utilizing the memory instead of the entire history of features. Isn't that exactly what's happening here? Right? You want the image, the mask decoder here, you want it to output the masks for this given image, but you also want it to be aware of the entire history of masks that have been created for this video. But rather than giving it all of the history of all the previous masks for every single frame that you have in this video, which would be a huge amount of information, you want to give it some compressed version of that. And that compressed version of that is what you're storing in this memory bank. So that's basically this. Token Turing machine. I hope that answers your question, Explorer. I don't know. All right, guys. I was wondering how long the external memory system RAG would survive when the memory is outside the box. So RAG, which is retrieval augmented generation, that's a much more explicit form of memory, right? In retrieval augmented generation, the memory bank is like literally a database of text, right? It's literally chunks of text that are indexed by some embedding. So you're storing the actual information of like, oh, here's an actual paragraph about the time the user liked coffee, and so now they're mentioning coffee again. I'm going to attach that little paragraph of text to the context, right? So RAG is not compressing that information versus this memory bank here is being compressed. You're compressing that with this memory encoder. And then this one here, it's also compressing that, right? It's not like it's storing explicitly all the video chunks and then indexing them, and then you're going and finding the specific video chunk related to that and then appending it to the current input. It's like compressing it down to some representation, some compressed version of that, and then that's what you're using to feed into the model. So I think you do need to do that. I think that the models of the future are, the memory banks are going to be not explicit information like in RAG, but like encoded information like this. Does that occlusion output help with predicting objects that are occluded during the video? Yeah, the occlusion thing is definitely for that. Right here, right? Occlusion score, right? So you can think about like, where does this occlusion score come in, right? So it comes out of this mask decoder. This occlusion score is part of what's in this memory bank. So whenever the memory attention here gets the encoded image, it actually knows whether an object is basically likely to become occluded or whether it's already occluded. So this mask decoder says, okay, there used to be a chicken here, but now I know from this memory bank that the frame right next to me, the chicken isn't there anymore. The occlusion is up, or the occlusion is 1, I guess, if 1 means fully occluded. Therefore, there's probably not a chicken here, right? The model, question from Explorer, the model inference memory VRAM grows with the number of users and the amount of memory it needs to keep in the context forever. Yeah, this memory is going to grow. So here it's fixed, right? So here you have a fixed number. So it's a FIFO Q with n frames and m prompted frames. So like there's a specific limit to this memory bank in this implementation of the memory that prevents it from growing too big, right? So there's a specific amount of GPU memory that's I don't even know if it's GPU. It might be in the GPU. It could also be in the RAM. So it's not necessarily in the VRAM. It could be in the RAM. But it's basically saying this chunk of memory is always going to be the same size. This memory bank is the same size, which is really what linear attention is, right? If you think of something like a Mamba or an LSTM, you're basically saying, okay, the memory is always going to be this size. The hidden state has a fixed size. So no matter how much shit, how much video, how long this fucking video is, it's always going to be the same brick of memory. The VRAM requirements are set based on model size, but with out-of-the-box memory, it becomes more dynamic, nuanced, how much memory it needs. Unless you explicitly limit that memory bank to some specific size, which is what I'm saying, right? And by encoding memories rather than storing them explicitly, then you can compress them, which means that you can now fit more shit in here. So that's why you need to compress it, because or else this would be just get too big. I don't know. Explorer, I would definitely recommend this Mirasol 3B paper because I think their particular implementation of this memory idea is pretty clever. And I think it's also what GPT-4o is doing, right? Because GPT-4o has some version of this. It has some kind of memory where it's storing encoded things and then pulling from that. Even if it makes it fixed, how does it work with more users processing data in parallel? Yeah, so you're talking about like in an inference use case, right, where this model's running in the cloud and you have a bunch of users that are sending requests and the requests are coming in batches. So the same way that there's some batch dimension to the frames that are coming in, right? So this image encoder, it's not running every single image individually, right? It's running images in batches where some images might come from some users and some other images might come from other users, right? It has some fixed batch size that it's running every time. So this memory bank, there's probably the similar kind of thing, right? Where there's some batch of memory banks and each individual user has some specific index inside that batch of memory banks. So adding more users is just adding an extra dimension to all of these things, right? So rather than having some specific size of shit going into this memory encoder, it's that some specific size plus the additional kind of batch dimension. Does that make sense? Kind of? I don't know. Yeah, I think the long story short, Explorer, I agree with you that there's a lot of different pieces here, and getting all of these to fit on a specific GPU, there's probably a lot of optimization you could do. Because I bet you with this type of thing here, right, they even mention it here that they use mixed precision, right? So I think down here they say we used mixed precision. Yeah, automatic mixed precision bfloat 16. So I bet you that there's different, I bet you that the image encoder versus this, like you could probably run different versions of these at different levels of quantization and precision and get different results. Like maybe the memory bank, you don't actually need a ton of precision there. Maybe this prompt encoder, you could actually use a heavily quantized version of this versus maybe the memory encoder, you want to use the full 16-bit, like, and then figuring out how to optimize that for a specific GPU in a specific batched use case for inference. There's a lot of engineering that you can do to make this run as fast as possible and as efficiently as possible on whatever hardware you're paying for it. But that's what engineering is, you know? It's figuring out what all those little magical numbers are. like these magical numbers here, the 32 by 32 grid. All right, guys, that's all I got. Thanks for the questions. Thanks, Explorer, Khalil, Jumpio, Swati, Caesar, Nuno, Patrick, 87GN, Kong, Christopher, who else? Vishvam, Jax the Ripper, Jeff G, Siraj, Fabian, Brian, Aditya, Sagar, Ed, Jonathan, and Sarah. Thanks, everybody. Hope you guys had a great time. Thank Aries. Thanks, Brian. And see you guys next week.